All right. Hi, everyone. Welcome to Starry Nights. Hopefully, this stream is actually going through now and you're seeing us online. If so, thank you for joining with us and apologies for the technical difficulties. My name is Matthew and I'm one of the staff members here at the Observatory. And if we've gotten this to work, which I believe now we have because I see the stream coming up, we are joined for the first time in audio by a co host, and that is Zena. So, Zena, can you please introduce yourself?
And I'm one of the staff members here at the Observatory.
Oh, I can hear you. Oh no, I closed it. Hi, I'm Zena. I'm the other staff member. I'm usually moderating, but this is the first time I'm actually projecting my voice. I'm excited to be doing this with Matthew.
Hooray! All right, glad we're all here. Perfect. So we've got a list of objects for tonight, and we do hope that the weather is going to cooperate with us. It sounds like it is going to. So we might have a few patches of clouds, but I've been trying out a couple objects. Zena and I were looking at a couple things here, and it looks pretty good to start with. And so we'll get going. So many people joined in. So thanks, everybody, for coming in. And we had 2 weeks in a row, which is amazing. Hopefully we get a couple more weeks of good weather before all the clouds start rolling in for the fall season. All right, so let's see here. So what we're going to do, we've got our first target here queued up. And what I'm going to do is, we're already pointed at it, so I'm going to change my exposure time. So right now in this mode, you can't see, I don't think, my adjustments I'm going to make. But what I'm doing is changing the exposure on an object, and what you're going to see is the binary star system of Albireo.
Nice. And we said Albireo is a visual binary star?
Yeah, we're not actually sure. So we've got a number of star systems that we're able to observe with our telescopes, but not all of them we are necessarily sure are true binaries in that they are actually gravitationally bound to one another. And so what happens is we can see them, and we might actually be calling them visual binaries instead of true gravitational binaries, because they may not actually be gravitationally bound to one another. They might instead actually just look close to each other but not orbiting each other. The particular difficulty with this binary star system is that their orbital period would be close to 100,000 years. So of course it's difficult to observe whether or not they're actually orbiting one another because no one has been around for that period of time.
Yeah, actually, I just realized we should introduce the moderators.
Oh yeah, we need to do that. So I got so flustered by our first streaming to the wrong stream that we didn't introduce. Zena, would you like to introduce our moderators?
I'm a moderator this time, so so yeah, we have Abby, and I think is it Ken?
Mm-hmm.
And Andra. Please welcome. They're gonna help you answer any questions you have.
Hooray! And I heard that Zena might be a little quiet. So Zena, I'm going to try to bump up your volume a bit on my end. And last time we got that to work, how did I do that? Here we go. Audio.
Yeah, I can. Let me know when should I talk.
Yeah, whatever you want. I'm just gonna make sure that people can actually hear you. So I want to make sure I'm trying to boost your volume as much as I can.
It looks good. I like the Albireo. It
Desktop
looks like
audio.
It's not as obvious as what if you were to look at it through the telescope, where you can see the bright colors, the blue and the red stars. But you can make it out. You can tell one of them is a blue, the other one is probably a red giant.
Cool. All right. Hopefully that helps Zena be a little bit louder. Is that better? Better volume. Okay, perfect. Hooray! So question, will they eventually drift closer or smash together? So these stars, if they are gravitationally bound to each other, we're not really sure what direction they're moving in right now. And so that's a really good question. Now, some binary pairs do eventually collide into one another. In fact, a cool story about most of the gold on our planet, and any gold that you have in your electronics. We use gold to plate electronic circuits for for conductivity. Gold was probably, most of the gold in the universe is created by neutron star collisions. So when neutron stars collide with one another, it produces gold. A lot of gold is also created in supernovas. So yeah, gold is literally star guts. And so if you have gold in any of your objects or household or jewelry or anything, the history of that is a stellar collision, which is pretty cool.
Oh, I didn't know that.
There you go.
It's pretty awesome.
Yeah.
Come from the supernova, from the star explosions.
Yeah, and from stellar collisions, yeah. So good question about these two. We don't know whether or not they're going to actually collide with each other because if they are tied together in a gravitational pair, they're so distant from one another that we can't really tell what direction that they're moving in yet. So we have a general idea of how far Albireo is. Albireo is also known as the head of the Swan or the Beak Star because it is part of Cygnus the Swan. So it's actually the star at the head. To the naked eye, this looks like one star, but through our telescope, we're able to resolve both of them. And one reason why we chose this object in particular, and if you've been with us at Starry Nights in person, you know that we often look at Albireo through our telescope, is because this binary pair in particular is so distinct in color. One is very clearly bluish in color and one is a yellow-orange, and that's because of the temperature differences on both stars. So temperature tells the star. The hotter the star, the bluer in color, the cooler in star, the redder or yellowy in color. And ours is kind of in the middle. Our sun is considered a yellow dwarf, but it's actually kind of more of a whitish color in that way.
That's very interesting. It's like the other way around. I think most people would think that red is hotter, or you would think red is hotter and blue is colder.
Yeah. Colors in space kind of work opposite that way. You can think of it as like when people say a flame is white hot or blue hot. So if you ever look at a blue flame, it's actually hotter. And if there's anyone in the audience that does film work, you will know that color temperatures on light bulbs are also given in Kelvin as well. And so that actually corresponds to the colors of light from stars. So you know that like a 5,000 Kelvin watt bulb is around a whitish color. That's kind of like the surface of our own star, because our star is about 5,500 degrees on the surface. Much hotter on the inside though. So there you go.
Yeah. Actually, if you use Bunsen burner, so if you're in science biology labs or chemistry lab, they use Bunsen burner. And the Bunsen burner, they give off a very blue flame. And one of the things I've noticed is that they can control the temperature of it, so they can produce a yellow or an orange flame versus a blue flame, and they would realize that the blue flame is much hotter than when they turn it into the orange flame.
Yeah, absolutely. And then Greg asked a good question. Maybe I said it already. Is the red one a red giant like Betelgeuse? No, this one is not a red giant star. It's probably more of like a yellow giant. So it might be on its way out. The age on this star is hard to tell because one of the things about Albireo is that the yellowy star that you see might also be a binary star. We're not exactly sure, but one of the problems about this star is that when you look at it spectrographically, and this is when you spread the light apart. Zita, actually, you were talking about spectrography, you were talking about it with me earlier. Do you want to go over like how spectroscopy works and how we can tell the ages of stars and stuff then?
Well, I don't know if you can. Oh, well, you can. So spectroscopy is the study of light because that's the only thing we can get. That's the only piece of information we can get from the stars. So with the light, we can actually. There's something called spectral lines, or you can think of them as prints or colorful prints. And with light, it produces a spectrum. If you remember, it's like the rainbow spectrum, and every element in the universe, or if you know your chemistry, the elements of the periodic table, each of these elements, when it's in a heated form, it produces a very specific spectral lines, or a specific, it's like a print. And so, for example, the spectral lines for hydrogen will look different than the spectral line for helium. And yeah, so that's how they can use the light that comes off from those stars to find out the composition or the chemical composition of those stars.
Yeah, and the chemistry of a star and also where it is in relation to other stars can help us to tell its age. So people are saying, okay, it looks like there are 3 stars on here. And so this one is not part of the group. It just happens to be in the frame of where our camera is. But these 2 here are part of it. But there might be one other star that's actually orbiting this one, the yellow star. And so we get some weird calculations as to what age it actually is, and that's part of the complication as to whether or not that star is a red giant or is on the way out. All right, so 420 light years, this pair of stars is. And again, we're not sure if it's a visual binary or an actual binary star system. Interesting thing, did you know, Zena, that most stars are actually part of binary or trinary or quadruple systems?
I was gonna point that out. So that was a lesson I had because I teach, so I'm becoming a high school teacher, and I'm
so
doing
exciting
right now. And I actually already taught the space unit, which is very exciting. So one of the things I got I picked up a number of stars, and I got the students to, there's like a star chart or a chart of star properties. And one of the things about when scientists or astronomers were trying to figure out the properties of stars, they actually struggled because most stars out there are actually binary, just like you were saying.
Mm-hmm.
So what I did is that I didn't mention that to the students at the beginning, but what I did is that I picked up a target of stars, and I got them to figure out how to put them on the star chart or the property chart. And they had to figure out if it's a binary or not.
Cool.
So that was a challenge for them.
So our sun just happens to be kind of one of the loners in the galaxy, because our sun is not part of a binary system. Although it was theorized at one part that it might have been, but but it doesn't look like we are. I know in the past there's kind of like a what's that? What's that? Sorry.
We're a special solar system.
Yeah.
There's only
So it might be, and I've heard theories, I don't know if this has been proven or not yet, but I've heard theories that actually might provide stability to our solar system, because when stars are in binary pairs, it might actually like disrupt the orbits of the stars in each planet and stuff. So I don't think there's a lot of research on that, but yeah. So Jason asks, is it common to be a loner star? No, actually. So it looks like most stars, we were just mentioning this earlier, it looks like most stars in the galaxy are actually part of multiple star groups, or binary, or trinary, triples.
I was thinking is that since we're in a solar system that only has one stars and there's life, so does that mean every solar system or out there that has one star likely to have an exoplanet with life?
I don't know. That's a good question. I know that right now the research that I've done, which is by no means extensive, but I've been doing a lot of writing. Started freelance writing for Universe Today magazine, if anyone's seen my articles out there. But I've been doing a lot of writing lately on habitable worlds. And as far as I know, whether or not a star system is in a binary, trinary, or quaternary pair with other stars is not one of the ways of ruling out life or not. So I'm not saying that I'm right. If anyone else knows out there, that's an interesting question. Now, in terms of star systems, Zena, you wanted to also look at Capella. Now, when we tried this earlier, it didn't turn out so good, because this is an actual quadruple star system. It's made of two binary pairs that are actually orbiting each other. Earlier when I tried this, my focus was not very good on the camera, so it didn't really work. But we focused a little bit better, so it might actually show up. So I'm gonna give it a shot and see what happens.
Yeah.
Let's see.
Because I know we were able to see
Technical difficulties. My name.
the actual telescope in the observatory. Or at least I've seen it before, or Howard showed it before.
Yeah. So the screen that you're looking at right now is a piece of software they use called the SkyX. It literally just shows the sky as it is right now. Not only does it have like the night sky programmed into it, but it also has things like satellites that are orbiting. We can turn all those on and off. These slits here that you're seeing show where the dome of the observatory is, which you can see moving around in the camera angles. And we are going to be moving to Capella, which is kind of on the other side of the sky. So here's where the telescope's currently pointed, and now the dome is catching up. The telescope can move pretty quickly, and I rotate about 180 degrees per second. So you can almost do a full rotation, 360 degrees.
Capella is a very, very bright star. It looks like it's a bright star.
All right, can we see it? Okay, there it is. Now, if I turn down the brightness, can we see the two stars? Let's see. I might have to zoom in here a bit. I don't think so. Now, that could be a function of our camera. The star might just be too bright for the sensor It might be overwhelming it.
It's beautiful.
It is very pretty though.
It's bright. Kind of reminds me of Vega.
Yeah. So, anyways, if we could see the other stars in there, just a little bit of details about the Capella system. It is a quadruple star system, so it's made of 2 binary pairs. 2 of them are bright yellow giants, and 2 are red dwarfs that are orbiting each other very closely, about 184 every 104 days. So, because they have an orbital period that's so much shorter than what you would get, say, with Albireo, we can actually study them and know that they are indeed orbiting around each other, because we don't need someone around for like hundreds of thousands of years to figure out whether or not, like, what direction they're actually moving in. And cool thing that I learned about Capella that I didn't know about at the time, although, oh no, did I lose my observatory connection? No, okay. A cool thing that I learned about Capella when I was studying it is that this was the brightest star in the sky 200,000 years ago when humans were first walking on the Earth. Isn't that cool?
That makes sense. 4 stars. 4.
Yeah, exactly, right? All combined together. And because, like, the stars, remember, we're all swirling around in the galaxy together, so the night sky isn't always the same. If you roll forward or back hundreds of thousands or millions of years, you get a totally different sky, which is pretty amazing.
Wow. So our ancestors 200,000 years ago, they saw different night skies than we did.
Yeah, totally. And totally different brightest star in the sky. Isn't that amazing? And then, like, in 14,000 years from now, as another example of how the sky changes over time, our North Star is not going to be Polaris anymore. It'll actually be Vega, which is so cool.
What?
Yeah.
Oh, wow. That's
Isn't that
amazing.
neat? There you go.
Is it because we're changing polarity? Yeah.
Yeah. So, yeah, that exactly. So, yeah, not only are the stars moving, but our planet wobbles around like a big top, right? So eventually the North Pole actually moves across the sky and points at different stars, which is amazing.
Wow.
Yeah. All right. Let's zoom back a bit more here. So yeah, unfortunately, it doesn't look like we can get that. I know that you wanted to check out Capella. Was there, well, when we were talking about it yesterday, was there something particularly about Capella you wanted to chat about, or why? Why were you eager to include it?
Oh, it's just because it's quadruple.
Yeah.
The quadruple, but you can, when I saw through the telescope, you can see only 2, like
Yeah.
the 2 stars. Like, you don't see the 4 stars, you only see the 2 stars.
Right. Yeah, because it's actually, and the 2 stars are actually 2 stars themselves, right? Which is,
Exactly,
they're
yeah.
so close. Yeah. I think with probably, like, to the human eye, it can probably make out the contrast better than our camera on the eyepiece can. I bet you if we did exposures, like a couple layered exposures of this, we might be able to point them out. But I think just to the camera, because it's, I think it's overwhelming it, which is why we can't make out the individuals. Anyways, something cool to know about Capella. Anyway, but why don't we look at something we can actually make out clearly? Since we were talking about binary pairs of stars and quaternary pairs, I figured, why don't we actually look at some star clusters? So what we're going to do now is move to what's called the double cluster, and these are clusters of new stars. So I think we tried this out last time I was hosting, and it didn't turn out so well, but I think we were having sky challenges this time. So let's see what happens. Here we go.
Double cluster.
So Zena, your background is actually biology, right?
Yes.
So
yes.
why the interest in astronomy? What brought you in this direction? I'm always interested in, because we always have such like a wider, most of people who actually work at the observatory are not astronomers, right? So, but I always find it interesting as to what brings them into astronomy. So what brought you in?
Oh, I've always been into, I think my first, I think it's since I was a kid. Like, we all noticed the stars and the moon, but what really got me really made me curious about the night skies is when I saw the Hale-Bopp comet.
Oh yeah.
That was very bright. Like, you can see it with the naked eye and you can make out the tail. And I was with my dad in the backyard and I asked him, "Oh, look at the star. Look at the star with the tail." And he said, "Oh, that's not a star, that's a comet." And then I asked him, "What's a comet?" And he didn't know the answer to it. He knew it wasn't it wasn't a star, and it wasn't rocky. So he just said, "It's a star with a tail."
Star with a tail. I like that.
And I went to look it up. It's like, oh, it's an ice. It's made of ice and dust.
All right.
So it started with a comet.
which is cool because we got to see a comet just a couple weeks ago, right, when Neowise was traveling through the solar system.
Wow.
Now,
The Neowise comet, and we imaged it too. It was actually very nice. Like we were able to image it with this telescope with the observatory.
yeah, that was really cool that we were actually able to do that. Okay, so we got there's images from the double cluster starting to come in. We're actually kind of looking in the center of them. So this is sort of one of the groups of stars, and the other one's kind of over here, and we're kind of staring down the barrel of the center. This cluster is 7,200 light years away, and it is made of 3,700 solar masses in total on one of the clusters, and the other one is 2,800 solar masses in the other cluster. And we had a question as to which constellation we're near. So I'll show you actually where we are in the sky right now. So we're in between Perseus and Cassiopeia. So that's where we are looking right now. And that's where the double cluster is located, right in the center between both. I don't know. I don't have the division up right here. There's actually like, there are maps that will show in the sky where the actual border lines are between constellations. So that's like in the sky, there's basically imaginary borders that show you or that denote where an object is, like which constellation it's located in. So double cluster is considered to be part of, these are things that I don't have memorized. Does it tell me here which one it's in? There's usually someone out there who knows. It's considered in Perseus. Okay, so that's where it is. So it's close enough that it's considered part of that constellation. So there you go. Cool. All right, let's go back. So what's the difference between Xena? Why are some clusters considered open clusters? These are two open clusters. Why are some globular clusters? Because we're going to look at those later too. What's the difference between them?
I think it has to do with the age. So globular clusters are you see way more clusters of stars, and they tend to be very bright because of the number of stars. So I think the globular cluster are much older, and they have been used to represent the age of the universe, while open clusters, because they're so clusters are just number of stars that are gravitating towards each other. That's how they form a cluster. So with the open cluster are the younger ones. So at some point the open cluster will turn into a globular cluster.
Cool. Yeah, so these are like very young stars. And so these clusters will eventually, they'll kind of dissolve with one another. They might end up becoming part of older clusters of stars later on, as Xena was saying. But so these are like relatively young. So these stars are probably about 13 million years old. You think about that, our sun is 5,000 million years old. So these are really young stars that have been born and are now finding their way off into the galaxy. They tend not to be gravitationally bound. So think of them like birds in a nest. Eventually, birds don't stay in their nest. They're clumped together in their nest, but eventually they fly apart and out into the air. And so this is kind of what open clusters are like too. When these clusters of stars form, they form together in kind of like a nest, which is basically like a nebula, and then they float out into space. So yeah.
So that's why if you were to observe the colors of the stars between the globular versus the open cluster, you should notice that the open cluster are mostly made of blue stars.
Mm-hmm. Yeah.
That also reflects in their age, because blue stars are the younger stars, while if they're more red or orange, then they are much older.
Yeah. Yes. Yeah, absolutely. Yeah. Cause like, we can also tell that too. That's a good point, Xena, because we can tell that as well by galaxies. Like the color of a galaxy will also tell us the age of the galaxy. So, because we know that stars the surface of stars tend to cool as they swell up toward the end of their lives. We can actually tell that some galaxies are really old because they're filled with old stars. They tend to be redder in color, which is pretty cool. Pride was asking whether or not they clump by chance. No, they formed together from the same cloud of dust and gas. So the same material formed all of these stars in the open cluster before they then head out into space. And so they form together. That's why they start together. And actually, I think it was just a couple of years ago, we happened to find a star that was so chemically similar to the sun that we think it's one of our siblings. We think it's one of the stars that formed in the same open cluster that the sun did, which is pretty cool.
Oh, nice.
Yeah.
Do you know so is that a close by star?
Yeah, I think it was I can't remember how many light years away it was. I wish I'd thought of that article before we started. I should go check it out. But if anyone goes online and you happen to Google like sister star to the sun has been found. It was a number of years ago. I think it was like back in 2018 or 2017. We found a star that was so similar to the sun that they were like, okay, this is probably one of our sibling stars. That's amazing. We know that we can find that out.
Nice.
Yeah. Okay. So
Are we looking at a globular cluster in this today? I don't think.
Sorry, what's that?
Are we looking in a globular? Oh, M15.
Oh yeah, we have a globular cluster coming up. I figured it would be a good contrast to this one, since it's hard to even tell you were looking at clusters of stars. Especially since we're looking kind of in the center of each of them. But if we compare that to, say, a globular cluster, you can really tell that there is a cluster of stars there. So there's one more.
Clusters.
Yeah, there's one more open cluster I want to check out. I think it might be a little bit more densely packed than this one, so it might be easier to tell that it's a star cluster, and that's the M52 open cluster. So I'm gonna try that one out next. There we go.
So what got you? I mean, I think I already know your story, but I don't know if does the audience know your story? How you got into astronomy? Because you're very, very knowledgeable of astronomy, but your degree is not in astronomy.
No, I'm a political scientist. Yeah, I'm not even a scientist. You're an actual scientist. I kind of play at science because I enjoy astronomy.
I tell my students everyone is a scientist whenever they say that, oh, I'm not good at science. Like, no, everyone is a scientist. We all started as scientists.
That is true. That is a very good point. I'm glad you said that.
I don't want to.
Because, yeah, I guess naturally everyone's curious, right? We want to learn about things. We want to learn the truth of stuff. We experiment. I'm thinking about when kids are like stiffing things in their face for the first time when they're young, they're experimenting. They're trying to like understand textures and smells and stuff, right?
Touching things.
Touching things, yeah. So that's a good point. Yeah. Oh, you asked. So how did I get involved? I think I've told the story. So for those of you who've been around, but when I was a kid, the one person in my family I really connected with when I was young was my grandfather. My grandfather was really into astronomy, and he had a cottage in northwestern Ontario, about 45 minutes out of Thunder Bay, where I grew up, in a lake called Shibandwan. And so he had his own cottage that he built out there, and the night sky was just like astonishing. And he had this little shaky 60 millimeter telescope, and there's no computer control or like any of that kind of stuff. It was just like on a tripod, and we would use it to go look at like the stripes on Jupiter. Actually, it was funny you mentioned, Zena. You talked about Comet Hale-Bopp, because I remember that's one of the things that I remember looking at through that little telescope was Comet Hale-Bopp, and trying to track it, without any computer, as it obviously moves really quickly across the sky and stuff. But yeah, he was the one who got me into it. And so I think for me, this is something I think about often, but I think the things that make us, that we are passionate about, are the things that make us feel more connected to ourselves and the universe and to those around us. So I think for me, space always reminded me of family because of him. And so, so that's why I really love astronomy. And of course, we always ask that question, of ourselves or, of other people around us, like, am I alone? Like, am I the only one who thinks like I do or feel like I do? And I think if you add that question up across the whole planet, well, that's what we're asking of space. Are we alone in the universe out looking for life?
Yeah. Space is philosophical.
Yeah.
And you can get emotional, spiritual.
Totally. All right. So yeah, this is the M52 open cluster. So you can actually see it's a lot more like densely clustered than when we were looking at the other one.
You can already tell they're kind of already gravitating towards there's like this area, the center, near the bottom right.
Yeah, these are, it's an older group of stars than the double cluster we're looking at. So it's about 158 million years old. And the radius from one side, or from the center out, is about 3 light years. So with the object that you're looking at, it's about 3 light years across. And it's a mass of about 1,200 stars. And one of the things that's interesting about this is that we can measure the light that's traveling from other parts in space, and to see there's something called that we can measure called dust extinction. And what dust extinction is that dust between us and an object extinguishes or extincts some of the light as it's traveling to us. So we can actually measure dust in the interstellar medium, we call it, between us and somewhere else, depending on how much of the light from a thing has been disrupted. And these clusters are a good way to do that because the cluster is so wide and we know about how many stars are in and how bright they are and generally what size they are, that if some of the stars appear dimmer than others, it's because there's parts of the light from the cluster that have passed through dust. And one of the things about this one in particular is that there's not a lot of dust in the center of the cluster, which suggests that it might have actually, like, a cavity has been blown out of the dust at the center of the star cluster, probably by supernova. And so if there are big blue bright stars, as you were saying, you know, they're young, but they also don't live very long. And so even in a cluster that's already 158 million years old, compared to our sun, these stars are young, but some of them have actually already died and blown up. And that's it. Even in a young cluster, they've already popped off. And in fact, that process might be necessary for other star formation to happen. We might need supernova within the gas clouds to explode because it helps to disturb dust so that it begins to form other stars, which is pretty cool.
Ooh. So that's actually really interesting, like dust extinction. So it's just, they just measure it by the light brightness or luminosity of it.
Yeah.
Is that what it's like, how if it gets, so they notice that it's getting dimmer and dimmer? I'm assuming that's how
Yeah, as the light is traveling across space.
But
Which
if
is
that
pretty cool.
absorbed by something, what if that dust was eaten up by some gravity?
Oh, well, this is
Matter.
This is one of the reasons why we're all waiting for that new James Webb Space Telescope to get out, because it can see through interstellar dust. It's looking at infrared, and infrared light can much more easily pass through like the dust that's in space, which is pretty cool. So it's one of the reasons that we're going to be able to peer into different parts of our own galaxy that we can't see because they're obscured by dust, or into the hearts of other galaxies, or even farther off into the universe, because of dust extinction. You know, this dust that eats up light as it's traveling through space. There you go. All right. You might notice if you're a bit of just a photography nerd, I'll point something out here. You can notice that there's these weird kind of faint edges that are forming along the sides of my picture. Anyone have any guess as to what that is? For 10 points in the chat stream. What is that? What's happening?
You talk about the blackness? Like,
Yeah.
why is it...
Yeah, there's like these blacker parts here. This is sort of a nerdy tech question. It's not as much to do about space, but let's see if anyone know. Any guesses?
I don't know if there's any photographers in the audience.
No? Any photographers out there? Any guesses? I'll highlight them so you can see them a little bit more clearly. You can see these edges. Yeah, it's stacking, exactly. So as D Runner is saying, so this is where the computer is rotating images to layer them on top of one another. So if you see here in the bottom corner that says that we have stacked 18 pictures. So right now, each of these images is 20 seconds of light that is being captured, and then they are stacked on top of each other to make one big 6-minute exposure. Each one of them is going to add time here. Now the problem is that the sky is rotating, but our camera is not. And so what's happening is the computer is moving and realigning each one of the images with the rest of the stars, which means that as the sky is rotating, these edges don't get as much data. There's not as much information being layered here. And so that's why these end up getting cut off from one another. But that's how space pictures are made. That's how we do it. Instead of doing one big long giant exposure, what we're doing instead is we're taking tinier exposures and then sandwiching them all together in order to make one longer image. And that's because everything that we're looking at is so faint. The light is coming from so far away. We're only getting a few little photons. I like to think of them as like drops. So if you imagine the telescope like a bucket, and that you've left out in the rain, the wider your bucket, our telescope's pretty big, it's 70 centimeters, it's going to collect more and more and more of that light, just like water filling a bucket. So the longer we keep our camera open, the more the picture is going to become clearer and clearer and clearer. So you know, how much imaging, so when you've when you've done photography at the telescope, what's the longest amount of time that you've sat there like photographing one object?
Oh my goodness, until 4 a.m. Because you usually start, I think usually we start because you have to first set it up, and then you do the actual image capture. So I think there was time when I started at sunset. I think it was around 7-ish to 8. It was in the summer, and then I just stayed until
the next day in the morning. I've done them multiple times actually. It wasn't just once. But I would say maybe the longest time I stayed at the observatory imaging was 4 a.m.
Oh yeah, right. So like hours and hours and hours, and that's what it takes. So if you any space picture that you see, this is including even the Hubble Space Telescope and stuff. It takes hours just to collect the picture. Never mind also then processing and everything else. It's not like we just have a camera and you take a snap and then there's like a beautiful space picture. We have to collect all the data for hours and hours and hours, and then you go home and you have to like process it and work on it. So I think one of my first astrophotos, like I think I watched all 4 seasons of Battlestar Galactica while I was editing that photo. So I think that's like 80 hours of editing time. So it's pretty common.
That was the Andromeda?
Yeah, that was the Andromeda one, the Andromeda Galaxy picture.
Yeah. I remember. Yeah, it takes a while. Like the real work is in the processing of the images, because you probably process not just because you have to look through all the stacks of photos, and you probably have maybe hundreds of them if you're doing it like if the longer the exposure. And you probably have to look through every one of them and get rid of the bad ones. Oh
yeah, we also like a couple. That's another reason why we do individual frames, right? Is that some of the frames get like messed up, right? And then like something like
a bird that flies through.
Yeah, exactly. Like I got photobombed by the International Space Station in like one of the pictures. It's just like this big bright beam like all the way through. It just happened to fly through that part of the sky. There's a question, isn't Battlestar Galactica a video game? No, it was a TV series. Well, I think there might be a game now, but it started as a TV series in the 70s. I don't know if you've ever watched the original one.
I actually thought you were talking about the video game.
Oh, really?
I was thinking about the YouTubers who
who stream the game.
I actually do that. I'm one of those type of people who watch YouTubers play video games.
Yep. Yeah. It is a game now, but it's based off a television show from the 70s and then restarted in 2003. Actually, it was shot, a bunch of the show was shot at SFU. Which is pretty cool.
Really?
Yeah, and I didn't know that. And then all of a sudden I started like, when I started working at SFU and I was like walking around and I was like, oh man, like these are sets from Battlestar Galactica. I was so blown away. It was awesome. Anyways, a bunch of the cast still live in town. I don't know if any of them are here.
That's awesome. Now I want to see so it's probably SFU from back then in the 70s then.
That was the original series. The reimagined one so there's 2 series, and the new one that was shot that started in 2003 is filmed at SFU. So the more recent one.
Okay.
Cooper says the original was really bad. It was a wee cheesy.
Did you see any scenes like, oh my god, I know where this is?
Totally did, yeah. Especially like the big pond, the big central pond at SFU. We basically, all of us nerdy friends, we'd all call it the Battlestar Pond.
Nice.
All right, we switched. So you were asking, or you were talking about globular clusters earlier. So here's a globular cluster. What can you say, Zena, about globular clusters?
Oh, well, where is it? Yes.
Has it come up yet? Has it started to appear? I think so.
Oh, now it is. Ooh, look at that.
This is the M15 Globular Cluster.
Isn't it beautiful? You get this is I like the contrast. Like I like how different it looks from the open cluster, because with the open cluster, the ones you showed earlier, they were more bluish stars, and this one you can clearly see they're more reddish or orange color.
Oh yeah, you can. That's a really good point. Yeah.
And you can tell from the age, from the color of the stars, you can tell their age.
Yeah.
You can with their age, and most of them they're all red orange, so that tells you that globular clusters are much older. And it's interesting, the person who suggested that we're not, because in the back in the days they thought the Milky Way was the only galaxy in the universe.
Mm-hmm.
Oh, sorry. Yeah, the Milky Way was the only galaxies, and so, but then there was a scientist who suggested who at least thought that there must be there. Or no, actually, no, that wasn't it. He thought that the solar system was in the center of the galaxy. Actually,
okay.
That's what I actually thought.
We all thought that for a while, right? That like we were, And
then until there was a scientist who studied globular clusters, and he thought if the Milky Way was in the center of the galaxy, then we should see an equal distribution of globular clusters around us, like in the night sky. But then he didn't see that. He noticed that they were only in very specific constellations, and they were not evenly distributed in the night sky. So then he concluded from studying globular clusters that the Milky Way was not in the center of the galaxy. Sorry, our solar system was not in the center of the galaxy.
Isn't that amazing? It's so cool. I think it's so fantastic that, okay, we were talking about Capella earlier and how Capella was like the brightest star for humans like 200,000 years ago. So in the last 200,000 years, we evolved to like, be humans. And then we like started developing technology, scientific techniques, the instruments of that technology to like figure out where we actually are in space and that we can do that. Isn't that crazy? That's crazy. Yeah, we know where we are in our galaxy, and we know where our galaxy is, and at every one of those phases,
near the center.
yeah, it's just right. At every one of those stages, we found out that we're kind of an insignificant star in an insignificant galaxy, and we're not even at the center of anything. We're not even at the center of our own solar system or our own galaxy or anything. But as far as we know, we are one of the few places in the universe that might have life. We haven't found it anywhere else yet, and so it's still cool. That we're able to even discover our insignificance. It is significant that we can discover our insignificance. I think that's maybe the best way to put it. So there you go. Okay, so we've got, let's see, we've got this one coming in now. We've got 3 minutes and 40 seconds on this globular cluster. A little bit about this cluster. M15 is 33,000 light years away, so a lot farther than some of the other targets we've been looking at. And like Zena was saying, we use globular clusters to map our galaxy. There's a halo of these clusters of stars that orbit around the center mass of our galaxy, and they are quite old. This is one of the oldest ones that we've seen in our own galaxy. So whereas the other open clusters were tens or hundreds of millions of years old, this cluster is 12 billion years old. So a lot of the stars here are probably on their way out. It is 360,000 times brighter than the total light, output of light from our sun. So that's a lot of starlight, and it's one of the most densely packed of the clusters. It's undergoing something called core collapse. So there is the central core of the cluster is actually starting to draw itself even farther in still, and there's probably 100,000 stars in the cluster. So that's a lot of stars. It's possible that clusters like this also have black holes in the center of them, which is, they might have like a...
Do we actually know there's a black hole, or is it just a theory? Is it mathematically?
We don't know for sure, but it's hard to see the center of the clusters. And if there were black holes there, they'll be large, but they'll still be small to observe. But when we look at the way that the stars were orbiting the center of these clusters and their motion, it is suggesting that you might have not a black hole or a supermassive black hole like you have at the center of galaxies, but you might have something called an intermediate mass black hole, where it's not, millions or billions of times the mass of the sun, but it might be like hundreds of thousands of times the mass of the sun, which is pretty cool.
Do you think, actually, this is a question, whenever I think about the globular cluster, do you think they already, do you think they experienced stellar collision? I don't think we've ever experienced or ever observed stellar collision, but do you think it happens in the globular clusters? Yeah,
that's actually a really good question. I haven't read necessarily about collisions in these clusters, but I'm assuming that it is possible. And so I'm not going to rule it out because I don't actually know one way or the other. I'm guessing that given the density of stars and clusters, it's probably possible they're colliding with one another. If there's any spacey people in the chat, and you know that for sure, do star collisions happen in galaxy clusters? I'm guessing it's highly probable, but let us know. I know at least that they might be, at the very least, it's theorized that you do have a black hole in the center, and so it might be consuming stars in the cluster in order to grow in its mass. And definitely you're going to have stars that are like, starting to die. And within the clusters as well, which is pretty cool. Yes, these things are pretty neat. There is a short story that I think was adapted into a novel by Isaac Asimov, and it's called Nightfall, and it's about a civilization that exists on a planet orbiting a star in a star cluster, and because the stars are so close to one another, and this is an actual phenomenon, it's always daytime. Like basically they can't see the rest of the universe. And so what happens though randomly in the story is that at one time there's an eclipse that just happens to block out enough stars in the sky to see the universe for the first time. And then as a result, like their whole society changes, right? Because it's like, they realize that there's a whole other universe out there. So I was thinking about that for us, like how would our life be different if we didn't know that there was more universe out there?
Actually, if you imagine if you were to live where there's no nighttime. how would they even picture the night skies? Like they wouldn't see the stars, but they probably can use radiation or radio uh, or any kind of other so like any kind of like some sort of form of radiation
Yeah.
you can actually use to tell what's in the universe, but they probably won't be able to see it if they were to live in daytime all the time.
Yeah, exactly. Oh, Steven's joined us. So Steven Hummel's in the chat. Steven's works at the McDonald Observatory, and we'd actually chatted back and forth for one of the articles I'd written for Universe Today. Steven has this amazing photo of something called a lightning sprite, which is a phenomenon that's created by lightning when it excites nitrogen molecules in the atmosphere. It creates like these like tendrily-like structures, and we discovered them recently in the clouds of Jupiter. That similar phenomenon happened in Jupiter, and Steven was doing some outreach with his observatory tonight, but he was able to join in. And Steven confirms that yes, stars do collide with one another in galaxy or in globular clusters. So thank you, Steven, for joining in. Steven said it was cloudy over where he is, so that's why he's joining us now. So thank you, Steven, for coming in. It's always good to have great other experienced spacey people in the chat to help answer these questions. Okay, where do we want to go next? Do we start looking at galaxies?
Yeah, let's do that.
Or maybe, oh, you know what? Before that, Zena, because I know this is one of your favorite objects, and we were talking about stars dying. So why don't we look at some dead stars and switch over to like the Dumbbell Nebula?
Oh yes.
Right. I know Dumbbell was one of the ones you wanted to take a look at. So I think it's still visible right now. So let's switch over. Another thing to note is that Steven is working on something called the Dark Sky Project. And
your colleague?
yes, because he was mentioning that things like cool, atmospheric phenomenon, well, not only the night sky, but also cool atmospheric phenomenon like lightning sprites are difficult to see because of light pollution, right? And that impacts all of our lives in astronomy is light pollution. It's so hard to get away from anything to actually see what's going on. So check that out, Dark Sky Project, and with the McDonald Observatory.
Dark sky. I'm gonna put it on Dark Sky Project.
Now, here we go. Okay, I've cleared our stack. So we're going to start. Otherwise, we'd end up stacking the Dumbbell Nebula on top of the previous data for the star cluster, and we don't want to do that because they would all be mixed together. So we're going to restart now, and I'm not seeing Dumbbell in there just yet. Am I in the right place, first of all? Yes. All right.
Where is that observatory? The Dark Sky Project? You said it's in... what did you say? Where is it?
So it's the McDonald Observatory, and it is at the University of Texas in Austin.
Oh, okay. Oh, there you go. I had to write that down. Okay.
All right. All right. So how's our picture doing?
I think it's still on. Oh, okay, never mind.
I might have to change our settings. So one of the things that we can change as well with our images is something called binning. So what binning does is it takes the full resolution of our picture and we clump some of the pixels together in order to make a brighter superpixel. And Ian is here. Ian McClellan is a observatory expert and has also done work with the planetarium here in town, and so he knows about McDonald's. As he points out, it's many kilometers outside of Austin, where obviously you have dark skies. So there you go. Whereas our observatory, on the other hand, is right smack on the outskirts of Vancouver, but that's so that all of us can go and enjoy it there in person. That's the point of that observatory. So I'm going to change our binning to bin 4 because we might then get a brighter view of a fainter nebula. So let's try that. And
well, I can chat a little bit about the dumbbell.
Yeah, please.
Get it in. So yeah, it's so there's different types of it's a type of nebula, which means it's made of gas and dust, and there's two types of nebula. There's a starburst nebula and a planetary nebula. So planetary nebula is it's the result of a star dying. So first, when stars die, there's 3 different fates. And so there's the low mass stars. So the low mass stars will go through a planetary nebula. And for
the high mass stars, those are the ones that either become a neutron star or a black hole. So they'll undergo supernova. But that one, the Dumbbell Nebula, is actually a planetary nebula, which means the stars will turn into it means the star was a low mass star and it will turn into a white dwarf. And I think it already has a white dwarf in the center. That's why you will be able to see the colors, the vivid colors of the Dumbbell Nebula. And the colors that you will see is actually the gases that's emitting or shedding from the star dying. And let's see if you can see it. And
yeah, it's starting to show up here. I can kind of see it. So I'm going to get a little bit more exposure time. I'll start playing with the stretch and the colors, and we should be able to get it to show up.
And the Dumbbell Nebula is actually one of the brightest nebulas in our night skies, and you can use you can see it with the binoculars. It's actually the second, according to my research, it's the second brightest nebula in our night sky. The brightest one, I think the brightest one is the Helix Nebula, but I'm not so sure, so don't quote me on that one.
Actually, that's a really good point, Zena. Is that when we do our nights like this, we will specifically pick objects that are pretty bright at this time of year to observe, because we don't have a lot of time to expose them on our cameras each before, in order to give you a variety of topics or objects. That also means that if you have a telescope at home, even if it's not like a giant telescope like ours, a lot of these objects you can still see on your own telescopes. And so if we're going through a list of things and you're like, hey, that looks pretty cool, I want to go check that out, you can't, even without necessarily having to leave the city. Obviously, it look better if you do, you can leave the city. But yeah, like things like the dumbbell, star clusters, especially the bright globular clusters, you can see those with your own telescope. So, go do that. Go take your telescope and look at space, because it's one thing to have the light show up on your screen, but it's another thing entirely to have those photons travel all the way through space, thousands or maybe even millions of light years, and meet your eye. Think about that. That one particle of light traveled all the way through space and it reached your eyeball. That was its journey to meet you, a living creature on this one planet orbiting our sun. And that's kind of astonishing.
Yeah, it's actually with the Dumbbell Nebula why I resonate with it too much, because it's what made me really think about the sense of time with space.
Oh yeah.
Because with the dumbbell, it's 1,227 light years away, which means it took 2,227 years to reach our eyes, the light that you're talking about. And I think that's just amazing. So I think about, wait a minute. So we're looking into the past. What we see in the Dumbbell Nebula, that was 1,227 years ago, how it looks like. So I'm thinking, if this was the present, how would it look like? It's probably maybe all the gas are already shed away. Maybe it got bigger.
Yeah, or at least expanded, right? That's one of the cool things too, is that at these distances, we can actually see the gases change with things like supernova explosions. We can actually track, the motion of the gas over time. So yeah, I'm just kind of stretching this one out. We can actually start to see the shape of the dumbbell now, and you can see the colors in the gas. The gases will breathe away from the white dwarf at the center at different speeds based on how heavy the gas is. So the gases at the outer edge tend to be redder because they're usually hydrogen and bits of helium, which are lighter than other gases like oxygen and stuff toward the center, which gives us other colors. So here we go. 1,227 light years away. It was found by Charles Messier. Someone asked about the Messier number earlier. I think someone threw it up there because I actually don't have it memorized off the top of my head. I love Messier, though. He's a funny guy because his whole list of things was like stuff he didn't want to find, right? So he's basically looking for comments, right?
Yeah, interesting. He was, and my God, he named a lot. And they say that people who did astronomy back then are the real astronomers, because they didn't have any fancy technology to look. They built their own telescope and they just observed the night sky. So they are considered the real astronomers.
Can you imagine that? Can you imagine Casina, why don't you talk a little bit about the Andromeda project that we did to replicate like the distance calculation?
Oh, Oh, well, wouldn't that be better to talk about it when we look at Andromeda?
I don't know if Andromeda's on our list, but I just thought it was kind of interesting what you're saying based on like real astronomers. Like we got to do a project like that.
Yeah.
And how cool that was. But imagine being able to discover something like that for the first time. Like what would it be like to discover?
So Andromeda back in the days, they didn't know it was a galaxy. It was another galaxy than our Milky Way. They just called it the Andromeda Nebula. But of course, there are always the scientists. They throw in ideas, and somebody throw in the ideas that we're not the only galaxy in the universe. There are other galaxies out there. And the first time it was calculated, it was Edwin Hubble. How he proved mathematically that Andromeda is another galaxy is by using there's a star called the Cepheid variable stars, and he just used those stars to measure the distance, and from the results he got, he found out that those stars, the variables, the Cepheids variable, are in Andromeda, and from there he found out that Andromeda is another galaxy.
Oh, isn't it cool? Imagine making a discovery like that. Like that's astonishing.
Long ago. It was 1925.
Yeah, isn't that nuts? So even just until like 100 years ago, we thought that our galaxy we basically discovered the entire universe just like in the last 100 years. It's amazing.
Moving fast. We're discovering more.
Astonishing.
We'll have to discover actually about the universe. There's like the dark matter, dark energy. We don't know anything about it.
I know. There's still so many things we don't know.
Just know there's something dark.
Something dark out there. And it makes up the most of stuff, which is astonishing. Okay, another dead star. We're going to do the Ring Nebula. This is always a fun one because it's quite bright. So we'll do that one.
You know, something about something about the dumbbell, because when I think about the time, I always like to know, okay, so when the light left from that object and reached our eyes, what happened back in the days?
Oh, what happened 1,000 or 1,200 years ago?
Yeah. So
okay.
I looked it up. I like to do that. So sometimes you get interesting information, sometimes nothing interesting. But for this one, for the dumbbell in particular, it's when the Vikings attacked the Old English Kingdom.
So there you go. That's when light from the star left to reach us.
Yes.
Wow.
So I wonder if they saw it then. So does that mean they didn't see this? They didn't have the Dumbbell Nebula then.
Depends on how long the star has been dead for. And I actually don't have that detail on Dumbbell. Like some stars,
they saw it different. I guess whatever the Vikings back then, they saw it different. Like it looked different than how we see it right now.
Yes, if the star had already died, like even if they did have a telescope to look at the Dumbbell Nebula, the nebula would definitely be a different shape because the gases wouldn't have expanded as much as they have over the last like few thousand years. Phenomena like that do happen. So for example, like with in Taurus the Bull is M1 the Crab Nebula, and that the supernova explosion that created the Crab Nebula was actually observed by people like 1,000 years ago. They wrote about it. So we actually have Chinese astronomers that have in their notes saying that they saw like a bright extra star in the sky, and that was the explosion, which is pretty cool. Okay.
So do we know what's the Crab Nebula gonna turn into? Do we know if it's gonna turn into a black hole or a neutron star?
Yeah, so the center of the Crab Nebula is in fact a neutron star, because as you were saying earlier, like the heavier mass stars, when they explode, they create different phenomena. So there is a pulsar at the center of the Crab Nebula, and we've actually been able to image it, which is pretty cool. And the waves of energy that are rippling off the Crab Nebula. So there you go. Stephen pointed out he came in with a save of the age of the star. So that M27 is about 4,000 years old. So that star would have died 4,000 years ago. So when the light left this nebula to reach us from the Vikings, it traveled that far in time. But even for thousands of years earlier than that, the star had died even before that.
So probably this would be a smaller nebula.
Yeah. And the progenitor star, so the star that did die to create the Dumbbell Nebula was probably about half the mass of our sun, so our lower mass star. Okay, let's move on to the ring, and then we're going to do some galaxies. So.
Oh yeah, if anybody interested, the Dumbbell Nebula is in the Vulpicula constellation, the little fox.
Oh, there you go. Thank you. And the ring is pretty close to it.
Know where the constellations are? because that's how you can make up. Like I know, I remember with when I was trying to locate the comet that came in the summer, the Neowise comet.
Yeah.
It's so nice. I looked up on Stellarium, and then I found out which constellation it is, and thankfully it was actually just, I think it was above or below the Ursa Major, and I was like, oh, that's an easy constellation to spot in the night sky, and it was accurate. I loved it. It was so accurate.
Yeah, I'm so bad with constellations. I'm my brain is really good at memorizing like scientific processes for things, so I could easily explain to you like how like a star forms or blows up stuff. But when everyone's like name constellations or which ones are up at this time of year, I can never remember that stuff. That's why I always got the app on my phone. I'm like, I don't know. And then people are like, don't you know this stuff? And I'm like, I don't remember.
Well, that's good that we have those apps. We all use smartphones. Might as well put them into good use.
Yep. Yes. That's why these apps are also so cool. Although I still have great respect for members of the Royal Astronomical Society. Some of them are here. So Ken's here right now, and I think Jennifer Kirky is here as well from RASC. But especially the people who come out when we used to do, and hopefully again soon, Starry Nights in person up at the observatory. And people from RASC would actually, some of them would bring up their own telescopes, and a lot of them are so experienced and just like, you know, they don't use computers. They just be like, hey, where's this thing? And they'll just like spin their telescope and point right to it. You're like, what? So I just have mad respect for that.
They're hobbies.
Yeah. Oh, yeah.
They're the experts.
The experts. I don't know. Okay, so we've got some data starting to come in from Ring. You can see it just faintly here. And I'm going to start playing with the picture and try to bring out the nebula.
The Ring Nebula is very beautiful.
Yeah, unfortunately, I don't know if maybe, I wonder if perhaps we're getting a bit of cloud or something in the sky, because the computer is not having an easy time stacking this picture. And I don't know why that is. So we might be looking at, there might be a haze in this part of the sky. Sometimes it's light. There's some new lights in and around the observatory these days, unfortunately, and sometimes if we're at a certain angle, some of the light will reflect off the inside of the dome and into the telescope. And when that happens, the computer is using the stars in the picture to align the images. And if it can't grab hold of the stars clearly enough, it's not able to make a stack out of the picture. So
unfortunately, we can't really close those lights that are outside the observatory.
I know.
Because of safety reasons.
Yes, that's part of it, I think, yeah. So right now, it's not wanting to do a stack on Ring. I'll try a little bit. I'll try to reset, and then we'll try again. I can also try to...
I'm looking for the image I processed with, because there's the one that Howard processed for the dumbbell, and there's the one I processed myself. And it's hilarious. Howard, when he saw, I was like, what? How long it took you to do this? And I told him, well, not as long as he did it.
Right.
And he was like, no, Zena, that's rude. You can't say that. I was like, Leo, don't say that. He's like, I spent so much time on editing his, and mine looked equally as good as his, but I didn't spend as much as he did.
I know. Sometimes you can luck out on a photo, depending on the quality of the sky that day or whatever.
It's like, well, you know what? Could be a great opportunity. You can do it the quick and dirty my way, and then if it looks great, then you can do it the hard work, the long hours way.
Yeah.
What's the opposite of quick and dirty?
Quick and dirty. The long and clean. Okay, it's stacking now. Hooray! Okay, so we've got 3 images. I could tell because down here in the picture it says the number of frames that have actually been stacked versus ignored. And so thankfully it's not ignoring any of the frames right now. So now we're adding to our total exposure time. So each one of these is 20 seconds. So 3 times 20, so 60, now 4. So we got 80 seconds of exposure. You can also tell here, this is this graph kind of shows data that's coming in from the light on the picture. So your kind of red, green, and blue visible light. The white line is kind of an overall color curve, and usually at the peak of the picture is kind of where your image actually is. The rest of this stuff can be attributed to like sky glow or the other stars or light pollution and that kind of thing. So when we're moving when I'm moving the slider over, this is the black level, and when this slider comes over, I'm literally like slicing parts of the data out so that we're getting down to what is the sky and the actual picture that we're trying to look at. So if anyone's wondering what I'm doing when I'm moving some of these lines around, that's in a nutshell, it's kind of what we're doing. What can you tell us about the Ring Nebula, Zena, since we're looking at it? You're our planetary nebula expert, so you did Dumbbell. What about Ring? What are we looking at?
Oh, actually, I did not. Ring was on my mind. It's one of the art objects I wanted to do. I actually did image it,
but it wasn't using. But I don't think I used not the colored camera. It's the one with the filters.
Oh, so our primary camera on the other side. Yeah.
And I can't find it because I have all the files. I just need to figure out how to use it on PixInsight.
Yeah.
So hard. Like I did learn it. It's not an easy program to use. It's not friendly user.
Yeah. What is PixInsight? You know.
It's an imaging software. It's like Photoshop, but it's like the Photoshop for astronomers or for photographers. And it's the thing with the PixInsight, it has a slow learning curve because it's for a very targeted audience. Like I think you know how to use it. You've actually you bought it.
I did. It was bought for me. So I had a group of friends of mine that were kind enough to go in and buy it for me for my birthday. And so I've used it now to edit a couple photos. I do like it. It is a steep learning curve. Steven says it's the bee's knees. I would agree. It is a really good software. But I think the challenges that we had with our observatory is that it is really difficult to get clean images of the sky just because of all the light pollution being so close to the city. So that's a challenge. Yeah.
I like when I see the ring. I just love that you see the different colors. You see the red on the edge, and then it's more blue. So that kind of it's consistent with what we see with the dumbbell.
Yes. Yeah. Same gases and stuff, right? So
because when you think about the stars, so the stars are made of hydrogen, and hydrogen, when it's in a heated form, it gives off the color red. So it makes sense. The first gas you give off in a planetary nebula will be hydrogen.
Then you go to I guess you have to. I don't remember what's the order on the periodic table, but usually you start with hydrogen, and then you go to helium, and then lithium.
And then the rest, right?
And then the rest.
And the rest. Yeah.
Until you get to iron, but
yeah.
But then I know oxygen. I think oxygen is in the bluish. It gives out that bluish color.
Yeah. And you can actually see the point at the center is actually the white dwarf in the center of this star.
It's actually very clear. Yeah, you can totally see.
My understanding is this star died about 2,000 years ago, and the whole nebula is about 200 times brighter than the sun. So there's a lot of light that's still coming out through all of the gas that's being illuminated by the white dwarf at the center. But it's highly likely that, like, in a few billion years, if someone takes a picture of our sun, this is what we'll look like to them, from a couple thousand light years away. So if anyone's around to take a picture.
So if they were maybe living where the Ring Nebula is, or the Dumbbell,
or maybe it'll be other humans that have evolved out in space somewhere, and then they're looking back on where they came from billions of years ago. Maybe it's still it'll be some legend of their past or something. Who knows? Sounds like a cool sci-fi idea.
Oh, someone asking what's a white dwarf. That's a good question. We talked about white dwarf, but we haven't really talked about what it is.
Yeah, sure, go ahead.
Diamond in the sky, diamond in space.
Yeah, shine bright like a diamond. Shine bright like a diamond.
White dwarf.
So yeah, white dwarf.
The scientific version of a white dwarf.
So a white dwarf is basically it's the crushed core of a dead star. So I'm being told not to sing. It's like, don't sing. It's why I have this condenser microphone at my house. It's because of all the lyrics I spit when I'm not doing space stuff. Anyways, so what is a white dwarf? A white dwarf is the dead core of a star. It's left over when a star has exhausted the rest of has stopped burning its hydrogen fuel in its core, and its outer layers are shed off into space. And it's usually like a ball of compressed carbon, actually, is what it is. So that's why sometimes white dwarf stars are considered to be giant diamonds in space, because compressed carbon is essentially a diamond. So yeah, they are old stars, like stars toward the end of their lives. So usually white dwarfs are billions of years old. And in addition, they will eventually cool down and turn into an object called a black dwarf, which is then no longer radiating any more heat. But they don't. That hasn't happened yet. The universe actually isn't old enough for any white dwarfs to have cooled down and stopped radiating their heat off into space. So that at some point in the future, that will be a thing. These other these other
what
objects.
about brown dwarf? I think we have observed, or we have imaged brown dwarf before.
Yeah. So brown dwarves are basically they're kind of like, some people consider them to be super planets and some people consider them to be failed stars, but they're basically masses of gas that are very, very heavy, but just kind of on the cusp of becoming stars, but not quite heavy enough to actually be stars. And so I tend to think of them as super planets rather than failed stars, but apparently that's not entirely accurate because they do tend to form at the center of star systems. And so, but yeah, they are objects that are not quite heavy enough to be a star, so kind of like a failed star.
They can't join the club.
They can't join the club. Yeah, you're out. You know how much Hydra did you have? I don't think you're allowed in. Okay, so all right, let's move on. What we're gonna do? Let's try. We're running out of time. I can't believe so much time's gone by. Okay, so you wanted to try Pleiades. You still want to try that? Is it high enough yet to actually try?
Let's look at Stellarium.
I think it is. Pleiades. Find. Oh yeah. There it is.
Did you know stars don't actually twinkle? That was some sort. I was shocked. That was a shocked fact.
It was a shocking fact. It's just our atmosphere lying to us.
I know, right? It's so they only twinkle in my eyes, but they don't twinkle in reality.
That is true. Yeah. Actually, one amazing thing that happened when I was down in Madras, I don't know if anyone else, I know some people went down to Madras to watch the solar eclipse in 2017. But when the moon was eclipsing the sun, and then you get that last little bit of sunlight that shows up, it starts twinkling. Like the last little bit of sunlight that's squeezing around the moon, it starts to twinkle. And it makes, because it's the main source of light that's around, it makes everything look like it's underwater because all the sunlight is twinkling. It was the most amazing thing I've ever seen in my life. If you get a chance, go see a solar eclipse. There's one coming up. It's going to be on the East Coast, and you need to go see it because it's amazing. And Dan, yes, we will look at Mars. I had it planned for the last thing to look at because
the one where it's like the one we saw was the one in 2017 that was a full solar eclipse.
Yeah, total solar eclipse.
But the one I want to see is the one where it's called the Ring of Fire.
Oh yeah,
that did happen. It actually happened this year, but it wasn't in North America. It was somewhere else. I think it was in Asia and Middle East. And I'm so disappointed. If I was planning to travel this year, but damn it, COVID.
Yeah, Ring of Fire. That's when the moon is a little bit farther away in its orbit. It doesn't fully obscure the sun, right? Is that what they call it, the Ring of Fire, when you can still see the sun around the moon? Yeah.
You see a ring.
Yeah, cool. So cool.
Yeah, I want to see that. That's that was supposed to be this year. I was supposed to travel this year, but
annular eclipse, Ian says. So Ring of Fire is technically is called an annular solar eclipse instead of a total solar eclipse. So thank you, Ian, getting our terminology right. Pleiades, we decided we wanted to do. It's kind of a bit of an experiment because Pleiades is quite large, and I don't know exactly what part of it we're going to fall on with the telescope. The whole thing doesn't fit into the telescope's field of view. Mainly we went here because there's a really cool nebula around Pleiades that's illuminated. It is an open star cluster like the earlier ones that we were looking at. Young star cluster. It's one of the closest to Earth, and you can see it with the naked eye. It's sometimes called the Seven Sisters. It's right near Orion. My mythology is really bad, but I think what it is that Orion is chasing the Seven Sisters and Taurus is kind of in between. Is that right?
I like the story behind, the story created for the Pleiades.
Yeah.
Like Orion, the hunter, he wants to marry one of the Seven Sisters, but they don't want to marry him, so that's why he's chasing them. And there's the Taurus, who's in between Orion and the Seven Sisters. So I think I think Orion is actually, you see him like if you've seen Orion, the Orion constellation, it's like he has a bow and he's facing it towards the Taurus, so he's fighting the Taurus so he can get to the Seven Sisters.
Yeah. Maybe he just he should learn consent and then just not, just let them go. Yeah. Anyways, so we wanted to see if the nebula would get picked up in our camera, and Dr. Wu, Joanna Wu, said we kind of ran that one by her, and she didn't think it would show up, and so I just thought we'd give it a quick look, and it doesn't look like it is. One of the cool things about that nebula, however, is that it doesn't look like it's actually part of the cluster. It might be just a portion of gas the cluster is currently moving through right now. So it's called a reflection nebula, and it's light reflecting off the gas in the nebula. But it's probably unrelated to the stars themselves. So that whatever gas and dust and material that form those stars, the Pleiades, has probably already dissipated off into space, and they themselves will float apart into the galaxy in the next 250 million years or so. Although a lot of them are very large class B stars, so blue stars, and so some of them might actually explode before that even happens. But anyways, it's 444 light years away. Pleiades, it's that little tiny cluster of 7 stars you see with the naked eye. There actually is about 1,000 stars in the cluster, but there's 7 of them that you can see very clearly to the eye out in front of Orion the Hunter. So go look at them. They're actually above the horizon right now, but this is not going to show up in the camera. So we're going to abort and go to something else. So let's try. We wanted to look at least one galaxy before it closed off, and then maybe try out some planets. So I am going to go swing over to one of my favorite galaxies of all time, M81, which is also sometimes known as Bode's Galaxy. And it is a beautiful, beautiful galaxy. When in my head, when I think of galaxy, I think of this one, because it's like the archetype spiral galaxy. It's so pretty. Let's see what it shows up like. I don't actually did look at it ahead of time, so I don't know how it's going to show up, but let's take a look.
I can't remember. I think I imaged one of them. Either M81 or M82. I
Yeah.
I just don't remember. Is it 81 or 82?
I know, yeah. Some people, I actually imaged it myself, but I
Huh?
haven't. Oh, sorry. I was going to say I took a picture of this one too, but I haven't finished processing it yet.
Is it an edge-on galaxy?
It's kind of on an angle. I don't know the actual angle.
Oh, maybe it's the same one than I did too. Because I was aiming for the cigar galaxy, but
Oh yeah, that's M82. So that's the one beside M81. They're pretty close to each other.
All right, let's see it. There's Sombrero Galaxy too. I know that we can't see it today, but I think it's one of the. It's a pretty galaxy.
It's also a very, very pretty galaxy. And there's some pretty galaxies out there. I think ultimately galaxies are my favorite objects to look at. Stephen was saying, "Wait a second, you can't see M81," and then realized we're up in BC, so we can see it from where we are. It's one of the reasons also why observatories will coordinate with one another, because we can all see different parts of the sky for different parts of the world. That's why we've got to work together. It's one of the reasons I love science and space, because it makes us unified. From space, you can't see the borders on the Earth. We're all just one group of people living on our little blue planet. Okay, how's this turning out? Let's clear that for now. Start from scratch.
Why is it your favorite? Why is M81 your favorite?
So I don't know how well I know that in our few minutes of exposing this, it's not going to do it justice. So I might actually pull up a photo of it so that we can see it. But I love it's called it's a spiral galaxy. It's one of the classes of spiral galaxies that are called grand design spiral galaxies, and it just has these beautiful spiral arms in it. It's such a pretty galaxy. So M81 is about 90,000 light years in diameter, so it's smaller than our galaxy, which is I've heard estimates now anywhere from 150 to maybe even 200,000 light years across. It's 12 million light years away. So remember, the light that left this galaxy is now arriving at us. It's already 12 million years old, and there is probably a supermassive black hole at the center of it that is 70 million solar masses. So the one at the center of ours is probably 4, so it's a lot tinier compared to that. If Joanna was around, I'd ask her why that is, because I know that
then a star, if it's that old, it's probably mostly made of old stars.
The galaxy itself is probably similar in age to ours, as far as I know. So it may not be full of old stars. When galaxies get really old, they tend to evolve in shape to become elliptical galaxies rather than spiral galaxies. So it's still there still is active star formation going on in M81. Not as much as in M82 though, the cigar galaxy that you imaged, because that's a starburst galaxy. So there's lots of stars being born in M82. All right, let's see.
Asking to adjust the image.
Yeah, I'm gonna see. We
And
have some
also,
frames.
we asked earlier if we can see Mars. So maybe after that, you want to see Mars?
Yeah,
Overall?
we'll go Mars after that. I'm gonna see how much of this galaxy we can actually get. it's kind of there. Look at that. Okay, so there's the core of the galaxy. You can see the curve of it here. You can see some of the spiral arms in there as well. And let me adjust my colors a wee bit. A little bit too much red in here.
So you already imaged it with the colored camera, or is it the one with the filters?
I imaged it with our monochrome filter camera. So I've got a whole bunch of data sitting around from it that I need to brave. But as you know, sometimes PixInsight is scary. So I haven't jumped in there yet with all that data.
Yeah, PixInsight. I spent so much time learning it, and then when I was away from it, I forgot. So now it's like I have to relearn how to use it.
Yeah, that's the thing, right? Is like sometimes if you're away from it for too long. All right, so here is M81. So there's the core of the galaxy, just like we have a core at the center of our galaxy. We are about 25 to 30,000 light years away from the core of our own galaxy. That's probably actually a good thing. Like stars have something called a habitable zone around them. So that's a distance away from your star that you need to be in order to have liquid water on the surface of your planet. It has been theorized or suggested that galaxies might also have a habitable zone. I don't know if that's been proven yet or not, but there's some speculation that you might have to be outside of the core of your galaxy in order to not be blasted by like a lot of radiation. There tends to be really old stars in the center of the galaxy. You've got a big black hole in the middle, and black holes can give off a lot of radiation if they start feeding. So it might be better for you to be sort of more out toward the edge than the core of your galaxy. But yeah, we're starting to see some of the circular shape of it here.
Nice. So it's a good thing. So I guess the reason there's life, we have to be at the edge.
We got to be at the edge. Yeah.
We have to live on the edge.
Living on the edge. All right.
Literally.
Literally life at
Not
the edge.
even figuratively.
Yep.
Living on the edge.
Living on the edge. Okay, while that's doing that, I'm going to bring up a quick picture of this galaxy because I want to make sure we give it justice because this galaxy is beautiful. So there's a Hubble Space Telescope picture of M81, and it is amazing. Now, keep in mind, this is after like lots and lots and lots of exposure time. So ours won't look like that right off the bat, but to give you an idea of what M81 actually looks like in a process photo, because again, it's one of my favorite beautiful, beautiful galaxy. Look at this. Look at that.
Are you showing it?
I am. I'm going to move it over here so you can see it a bit more clearly.
You kind of you can see some of the arms. It's kind of interesting. You can't see the details, but I think you can somewhat tell.
Look at that nice spiral. Yeah, so we're getting some of it. It's starting to show up. But, you know, if we had hours and hours and hours, eventually we could get ours to look like this. But in the time that we've got, so you can see, it's not quite the same angle, but there it is. That's the center core of that galaxy. But yeah, M81 is gorgeous. It's a gorgeous, gorgeous galaxy. All right, so we'll end on Mars. Does that seem like a good place to go?
Yeah, let's do that. Let's
right.
do Mars.
Let's do Mars.
What are your requests?
The reason why we waited till the end is that Mars has been getting higher progressively through the night, so we could get even a clearer picture of it. Because earlier we actually tried it in the evening, and it was still pretty fuzzy. When stuff is lower on the atmosphere, it tends to be in more air. So you're actually looking along the Earth's surface through more air than if you're just looking straight up. And so a lot of the image is distorted.
That makes sense. Okay, that's a good way to end it on Mars. Because last time when we did I think with Rohit, he did Mars first, and then later on people showed up, like somewhere near the end of it, and they were all asking about Mars.
About Mars, and it had already happened.
Yeah, we already looked at it, so I think it's a good idea to look at Mars at the end. Okay, let's check out Mars.
Okay, so let's change our profile.
So I have a philosophical question for you, Matthew.
Oh, okay.
So
yep.
Have you heard of the One-Way Mars mission? I'm sure you have, right?
Yeah, actually, my understanding is that they got canceled.
Yeah, I know. Did you apply for it?
I did not. No, I maybe I should have.
I actually did.
Oh, did you? That's awesome.
Back then.
So is the question? Were you going to ask me whether or not I would go if I knew it was one way? Is that what you're going to say?
Well, you already know my answer.
Well, yeah, you would. Well, why is that? Why would you be willing to take a one-way trip to Mars?
Are you kidding me? It's a free ticket to space.
Yeah, it is. Yeah, but it's a one-way ticket to space.
To go to space, and I'll make the history books.
You would. Yeah, that's true.
I mean, okay, it's okay. We're all gonna die one day. That's part of life.
Yeah, so you might as well go out like in a
Why
good way
not die on Mars
on Mars.
or in space.
That's right. Yeah, I think that makes
I
perfect
won't
sense.
be young. Like I think it's they. When I was reading on it, I think they closed the application. I think 2016 when they closed up the applications.
Yeah.
And that's when they started the training. So the training I think lasts for 10 years. So I've had like it's okay. I've still lived a good. I would have still lived a good life on Earth.
Oh yeah, of course.
It's not like I'm leaving to Mars young. I'd have still had like my master's degree, maybe even be a teacher.
I always thought that if you could only go once or like in one direction, then maybe the people who had figured it out hadn't figured it out enough. You know, like I would be more trusting of a company or a government initiative that knew that they had a two-way trip figured out, because I think that way they'd maybe put more thought into it. I'm not sure. I would still be tempted to go, but I would like to know that at one point I'd be able to return and come back one day. There's.
I'm thinking like if I'm going older, then yeah, I'll go. Why not?
Yeah.
If by the time I end the training, I'll be maybe in my 50s or 40s. Like I'll go.
Yeah, why not? I mean, for sure, I'd totally have to go. Now, I was actually going to ask you about this, Ina, because your background's in biology, and right now we have a mission that's going to Mars called Perseverance. There's another one that's being sent by the European Space Agency that's also going to be looking for life. So Perseverance is looking for probably signs of past life, more fossil life, whereas the new mission that's being sent by the European Space Agency is going to be digging to depths within the soil that would be protected from radiation, where you still might find microbes and stuff. But as a biologist, do we know anything about what alien life might be like? Like how would we even know, you know, if we found something on Earth, if it were alien or not? Like how do you make those distinctions? I don't know. I don't really know a lot about biology.
Actually, I don't know either. It's just about like where are we made up? Like carbon is one.
Mm-hmm.
Water represents life. Carbon represents life. We are made of carbon, and our DNA is made of nitrogen. So I think I would say those two are the main components of life: carbon and nitrogen and water.
Right. Yeah, water.
That's the thing. It depends. Like, do you consider whatever, like, if all the organisms that are like us are considered life, are part of life?
Then life is pretty diverse, right?
You don't even know if, like, are the aliens, they may not be made of carbon and nitrogen. They might be made of something else that we can't even comprehend or see.
Whoa. That's nuts. I'm excited. I'm excited to know that in our lifetime, we might actually have an answer as to whether or not anything's living on Mars. That's pretty cool.
You know what? There was one time where they actually, they said, there was an article, but I think it turns out it was inaccurate, where there was like a worm on.
Oh, the meteor. Yeah, it turned out it was just some kind of like feature from the heat or something.
Yeah, that's the one.
Yeah.
I was pretty excited when I read that.
Yeah, totally. Yeah, I remember that happened, and then they were like, we found life, and then it turned out not to be. So this is Mars right now. I think it's there's still a little bit of atmospheric disturbance, of course. Planets are actually really hard to observe directly because they're always moving around so much in the air. When we're looking at nebula and stuff like that, like in the amount of space that they take up in the sky is much larger than individual planets. So it's actually pretty hard to get a really crisp image of a planet without a process called Lucky imaging. And what Lucky imaging does is it literally does a recording of a planet, and then you spit out all the individual frames of the video that you've recorded, and then the computer will pull out the one lucky moments where the planet is in focus through the atmosphere, and then layer them all together. So when we're just looking at it live like this, it's going to be pretty hard to get really good features on it. But there's Mars. You can actually make out some of the different colors and stuff on the surface. So there it is. The fourth.
I wonder if anybody did it when I was in opposition. You know, there was that. You remember that day? I think it was 2 weeks ago.
Yeah.
Opposition.
I bet. I saw some really cool photos of people had taken online of it, so it's pretty awesome. But yeah.
That is awesome. Yeah. Actually, one of the things I just learned today, not today, but I learned about Mars is that they have blue sunsets.
Oh yeah, you were mentioning that. So yeah, tell us about Martian sunsets.
Yeah. So what happened is that because Mars is made, you know, it's red. So what happens that when there's a lot of carbon in the atmosphere, or carbon dioxide in Mars atmosphere, and carbon dioxide absorbs more of the red, and that's why and it gets reflected in their skies. That's why the Mars skies are pink, while we have it as blue. So because the carbon reflects the the pinkish red in their skies, it lets the blue color through, and that's what it is. The blue color that goes through the atmosphere that's reflected in their sunsets.
That's awesome.
And Earth, it's the other way around. It's like the blue color is the one that gets reflected on the skies. That's why we have blue skies, and the red color is the one that gets through. So we end up having the red-orange sunsets.
Amazing.
The blue sunsets.
Can you imagine that one day that's going to be on someone's Instagram feed? If Instagram's still around, whatever the corresponding social media is, someone standing on Mars, taking pictures of a blue Martian sunset.
Oh, that would be amazing. If you
cool?
were to sign up to go to the One Way Mars mission, why not?
Yeah, that's right. Or one of whoever ends up getting there first.
Yes. So
Yeah.
if they would open this again, would you apply?
Not for that program, but I would, if anyone would take, I don't know what skills I really have for an expeditionary mission to Mars. I'm sure later on at some point on Mars they'll need someone who can I'm just thinking about my other thing that I do is science outreach and education, but I'm imagining that anyone's on Mars probably already is pretty set and interested in science. But
there was 6 Canadians who made it, because it's all the application is opened all over for everyone in the world. And I think there were 6 Canadian who made it to the final list.
That's awesome.
And one of them, I think there was a doctor, there was a teacher, there was a pilot, and I can't remember the rest. But yeah,
Awesome.
It's all variety of people. It's not a specific career or specific. Yeah. They were they were considering everyone.
Well, one of the things I really am grateful for is that I through the planetarium here, the H.R. McMillan Space Center, I got to do a lot of outreach to elementary schools and meet so many young kids who were just so stoked about science and exploration. And I always wondered as I was doing that outreach if one of them would end up on Mars one day. And that's why I always told them, I was like, hey, remember that there was some wacky guy with glasses and an inflatable planetarium who told you about Mars. If you get a chance to go, make sure you bring me with you because I want to come. I want to go too. But anyways, on that note, we should probably wrap up because we're already at 5 minutes past 9:30. Thank you so much, all of you, for tuning in to Starry Nights. We will keep everyone posted on whether or not we're running the show again next week. How do you know about that? You can either sign up for our email list. You can check out our Facebook page. We're always posting updates there too. And there's also the meetups, which I saw earlier we need to adjust. So apparently we had an earlier time on that. So I apologize for those of you who came in earlier. But yeah, thanks always for doing this with us. We have so much fun doing this with all of you, and it's great that we have a chance to do it even in spite of everything that's going on with the pandemic. So thank you for transitioning with us to virtual, for being online, and for still enjoying the night skies with us. So on behalf of myself, Matthew, and
Nina,
thank you so much. Oh, sorry, go ahead.
Oh, sorry. I was just gonna say thank you to the moderators.
Oh, yes.
And Abby for helping us moderating and answering questions.
And we will hopefully see you all very soon. Keep looking up.